So today we move into chapter 6, which is entitled Introduction to Convection Heat Transfer. I encourage you to take a look at the outline of a section of a textbook. Can you tell what's going to be emphasized first? Boundary layers. Have you used the term boundary layer before, seen it before? Yeah, that's in fluid mechanics, and so it's a big review of what you had in fluids. And then if you remember, there was a whole discussion in fluids about local values, average values. So we repeat that discussion as a review. Then we talk about laminar flow, turbulent flow, a lot of repeat of fluid mechanics. And then we're going to talk about boundary layer equations. What are the equations which allow us theoretically to numerically or analytically compute that profile in the boundary layer for both our velocity profile as well as our thermal profile. These are governing PDEs, partial differential equations, with the appropriate boundary conditions. Numerically or analytically, we can solve them. Conservation of mass, then your momentum equation, and your energy equation. Then we take a look at similarity. That was a term we emphasized in fluid mechanics as well. It's like this system is similar to that system, and what we're going to find is for the momentum transfer is very similar in certain cases to the energy transfer. So we have this velocity profile is very similar in shape to the temperature profile in a boundary layer. And we build on that to, in terms of dimensionless parameters, coming out of fluid mechanics. What was the number one dimensionless parameter emphasized in that whole class? The Reynolds number. We're going to do it again. We're going to see it now for the next few chapters. It's very important, Reynolds number. But also we had skin friction coefficient in your fluid mechanics class. And we're going to then have parameters associated with heat transfer in addition to the fluid mechanics. Again, the fluid mechanics is something like friction coefficient, Reynolds number. We already were introduced to the prandtl number, and one other number, nusselt number. We're going to see the nusselt number here. This is the big finale. There's an analogy. There's an analogy attributed to Reynolds, who developed it and been modified by other people in the literature. And this is how the equation looks. And you're going to start to see this form popping up in the next few chapters. Say, oh, here is a correlation. It's pretty abstract because it has dimensionless parameters in it that describe it, but it makes it very general, broad. It can be applied to a lot of cases. And, oh, by the way, let's pay particular attention to some restrictions. Please don't take this correlation and apply it outside of the range of this prandtl number. So this is probably the biggest equation to come out of this chapter. So as you can see, what is C sub F? Friction coefficient. All right, what is RE? Reynolds number, two things you're familiar with. What is the prandtl number? New in this class, but we introduced it a few lectures ago. Prandtl number, nu over alpha. And then the new one for this chapter, I don't think we've seen the nusselt number before this chapter, have we? So it's a new parameter, and it's going to be defined. Let's jump into it. Hopefully that's a good roadmap where we're going. In review, let's start with our velocity boundary layer. We're going to start with a knife-edged plate. Why don't we start with a blunt plate? Well, if you have fluid flow approaching the knife-edge plate versus the blunt plate, if you have a blunt plate, what's going to happen right in this region of the blunt plate? You'll have some separation. The flow that wants to go here is going to have to scoot up and kick out, and then you'll have a separation region in there. So we have a knife-edge plate such that it's so thin, it's like a razor blade thin knife-edged plate. And so the flow cuts below and cuts above, and we don't have this separation at the tip. All right, that's probably, some people probably show flow over a flat plate, and they just sketch it with too thick of a plate, right? I'm probably sketching it too thick right there. All right, so now what happens to the fluid if it approaches all at uniform velocity, u infinity? Sometimes the book uses cap V For the free stream velocity, sometimes it uses U infinity. I'll probably use both, sorry. Okay, but cap V or U infinity. Well, do you have a no-slip boundary condition for that stationary plate? Sure, that's our traditional no-slip. It's so we have a viscous fluid flowing over this non-moving stationary plate, and the velocity at the surface of the plate is zero, no slip. So what happens is, because of the influence of viscosity, some of the fluid is slows down as it flows over. And there's this region which the presence of the plate is felt into the fluid. That region is called a layer, a boundary layer. Outside of it, let's say I go down to this location right here, and I just go out everywhere and I just say, show me what the velocity is out here. What's the velocity out here? What's the velocity out here? Well, guess what? It's all cap V or U infinity. It's still the free stream. It hasn't felt the presence of that plate. But as I get closer and closer, all of a sudden, it has to go to no slip boundary condition. It has to go to zero speed at that surface of the plate. And so this is the region in which the presence of the plate is felt. That's called the boundary layer. So everything underneath that line, how far up is that line? Well, first of all, let's introduce coordinate system. Our traditional coordinate system is to start from the leading edge and measure x, the horizontal coordinate. And then y will be the coordinate system going from the plate out into the fluid. All right, right away, what is the range of x? 0, 2, and we're going to talk about a finite length plate L, so it goes 0 to L. I know it could go 0 to infinity, but usually it's 0 to L. From the leading edge to the trailing edge. Then what does y go from? Does it go from 0 to some finite, or does it go off to infinity? Yeah, it theoretically goes off to infinity. But all the action is in this layer. Once I'm past that layer, it's kind of boring. It's just the free stream velocity. All right, so that's our coordinate system. So we think about going to this location right here, and we want to measure going up delta. Delta is our symbol for our thickness of our boundary layer. Isn't it? Are you familiar with thickness of the boundary layer, delta? Now, here's our first clicker question. Is delta a function of x, or is delta a function of y? Answer A if you think it's a function of x. Answer B if you think it's a function of y. All right, let's stop it. All right, so let's show our results. What does that say to me? We're either guessing or we're lost this early in a big lecture that's a very important lecture. I don't know what to do on this one. This is a review, true? Let me do this. If I move to this location right here, let me put this away for a second. If I move to this location right here, versus this location right here, did I change x or did I change y? If I go from that location to this location, that location, what am I changing? I'm changing x. All right. At every one of those locations, I have a thickness of the boundary layer. True? As I increase, what is the direction of increasing x? Horizontal toward the right. True? Do you want to just grade it? Let's just grade it instead of redo it. So the thickness is a function of x. The boundary layer thickness is a function of how far I am from the leading edge toward the trailing edge. And it gets thicker as I go. What is the criteria for how big the boundary layer is? How many people, anybody Can you remember what the criteria is? It's how far out I need to go such that the velocity is within so much of the free stream velocity. 90%, 80%, 99%. So if I go if I go out to a distance y, where that's equal to the thickness of my boundary layer, that's when the velocity will be so much, some percent of u infinity. This is how we define it. So let me do this. I'll ask another clicker question. Is it 99% or 50% or 1% of the free stream velocity? Answer A, answer B, or answer C? All right, I'm not trying to be hard, and I'm a little perplexed what to do. I thought that was not even underhand softball. I thought that was more t-ball style. When you have children, sign them up for t-ball. It's a blast. Right? So you put the little ball on the stand, they walk up with the bat, whack it, and it's in the play. They get to run to first. All right, anyway. I don't know what to say. It needs to go out. When you get out that far, it's almost u infinity. How much is almost? 99%. See, this velocity u is, let me back up. Maybe I forgot. We have u I plus vj plus wk is equal to my vector velocity. What does u represent in that equation? The x component of the velocity. It's in the x direction. I know there's a slight v kicking it up because of the presence of the plate, but typically that's neglected in the momentum equation. All right. All right, so our x direction velocity, when it's 99% of the free stream, we say, well, that's the extent of the boundary layer. And so that's the thickness, delta. All right. Now, somebody's going to come along later, and I'm going to say, you know what? I want to introduce u asterisk, and that's going to be u divided by u infinity or u divided by cap v, the free stream velocity, either way. Can you see what u asterisk goes between? U asterisk. What at y equal to 0, where is y equal to 0? At the surface of the plate. What is u asterisk? 0. And out at y a little bit greater than delta or above, y greater than or equal to delta, what is u asterisk? 1. It goes between 0 and 1. All right, very good. Now, inside this boundary layer, we have viscosity playing, and we can make a little cut like this, and we can look at how the fluid below this cut, at this location y, pushes on the fluid below that imaginary plane or cut in the positive x direction due to viscosity. And we can look at how the fluid above pushes on the plate to the fluid to the right, and below it pushes on the fluid above it to the left. It tries to slow it down. So the fluid on top is trying to speed it up. The fluid on the bottom is trying to slow it down. The fluid above it is trying to be slowed down. And there's an equation for this tau. What is the symbol tau used for? Shear stress. Okay. And that equation for tau is mu du dy. What is that equation? Law of viscosity. And so if you have a steep gradient there, if u is changing rapidly with respect to y, for the same viscosity, you'll have a larger shear stress. Tau is proportional to both the viscosity, mu, and du dy. Now, we're very much interested in tau s, subscript s. What do you think that subscript s means? at the surface. So this is tau at the surface, which would be mu du dy at y equal to 0 at the surface. Isn't that where the surface is? Y equal to 0? Okay. So we're very much going to be interested in computing. Now let's take a look, and I'm going to try and draw the location of the boundary layer at this location. And here is u infinity. I'll try and draw it the same. And then it comes in about right there and then does, or I'll go out to this location. Maybe I'll even move it further out. Let's move it out to this location. And this is all u infinity. U infinity doesn't change. But when it gets to the presence of the boundary layer, then I have to change from u infinity down to 0. True? Okay. For either case A, which is close to the leading edge, or case B or case C, farthest away from the leading edge, which one has the largest tau sub s? The largest shear stress at the surface. And let's try and show this one. Okay, so it's going to be A. Why is it A? Why does A have a larger shear stress than B or C? Is the viscosity different? Or is it the rate of change of U with respect to Y different? And here I can try and draw it with the red line. There's a slope. There's a slope. Let me just get this out of the way. And here's a slope, right? But as I foresee, as I'm changing Y right at that surface, the rate of change of U isn't as rapid as I move away from the plate. But here, if I move a little bit away from the plate in Y, the velocity changes much more rapidly. It's larger, that derivative is larger at the front of the plate, near the leading edge. All right, the last thing I need to cover was what is C sub f? By definition, what you do is you normalize the shear stress at the wall, at the surface, and you normalize it by 1/2 rho u infinity squared. Only a volunteer in the second row, not the first row, not the third or beyond. Only a volunteer in the second row, Zach, you're not a volunteer, can tell me what is the name of 1/2 rho u infinity squared. What do you call that term out of fluid mechanics? Was that out of the second row? Did you give me the answer? Yeah. Do you know what it is? Who did you? 1/2 rho u infinity squared. It's almost as important as the Reynolds number coming out of fluid mechanics. It dictates and it describes how the pitot tube works, the pitot-static tube. Who's heard of the pitot-static tube in the second row only? I don't see any hands. Everybody in the second row, write down the name of your fluids instructor. I want to know. I'll talk to him. Serious. What's going on? You don't know what a pitot-static tube is? The dynamic pressure. Congrats. That's all I'm trying to do. I'm not trying to rip your fingernail off of your hand, your finger. I'm not trying to torture anybody. It's a dynamic. Don't look at me like you've never heard of it, or the pitot-static tube. Serious. If you guys don't know your fluids, or girls don't know the fluids, you're coming out of fluids. What are you going to do? You need to know this. All right. So this is our skin friction coefficient, and I need to really get going here because I got a lot to cover. So this is the type of thing that we should be able to reproduce pretty much from memory. So you talk about your free stream velocity, your boundary layer thickness, the wall shear stress, and the definition of coefficient of friction. All this I developed, and within that boundary layer, U is a function of Y. The velocity profile is a function of Y for a given X. All right. Now we talk about the thermal boundary layer. So we do the same thing. We have this knife-edged plate, but this time that plate's going to be, you can make it cold and the fluid hot, but I think it's easier to make the plate hot and the fluid cold conceptually. So we're approaching it, and what type of temperature profile do you think you would make it easy? You'd put it all T infinity, all of its isothermal fluid approaching a hot plate. Where here, the T infinity is less. Well, the same idea, you're going to have a region at which the temperature of the fluid's been affected by the presence of the hot plate. And then beyond that region, it'll still be T infinity. So you come out, maybe we come out this far, and we say, okay, what's the temperature out here? All T infinity. Constant T infinity. You come into this right in here, it's a little hard to draw, but then you're going to have to go to the surface temperature of the plate. Here we're showing temperature, just like we did velocity, kind of on a length in the x direction for that snapshot at that location. So maybe this is TS, and then we have a profile like this to T infinity. That's our thermal profile, and we define this as our thermal boundary layer. So we come out, we say, well, how thick is that? Well, we use the same symbol, delta, but we don't want to be confused with the velocity boundary layer thickness and the thermal boundary layer thickness, so we put an additional subscript on there, somebody from the second row only. What subscript would you pick to distinguish between the velocity boundary layer and thermal boundary layer? What additional subscript would you put on it for the thermal boundary layer? T, you're brilliant. I'm going to help you recover your confidence. So there you go. So you have both the thickness of the velocity and the thermal boundary layer. What do you think is the criteria? Something like 99%. 99% of what? To getting back to where you were. So you introduce a T asterisk or theta. It's like T minus TS divided by T infinity minus TS. It's the temperature difference maximum, and then you have the actual temperature difference. What is T asterisk at y equal to 0? Is it 0 or 1? Answer A or B. Last clicker question for today. What is T asterisk at y equal to 0? It's 0 or 1? At y equals 0 is the plate. All right, I think I have to call this to an end, and let's grade it. Well, I'll just talk as if you're all understanding me. But unfortunately, some of us are not. Isn't T at y equal to 0 TS? Then TS minus TS in the numerator is 0. And okay, maybe I should let some people redeem themselves, huh? How about at y greater than delta T? Do it. Okay, one more clicker question, please. At y greater than the boundary layer thickness, what is T asterisk? So one person's playing with me. No, more than one is playing. 4 people. 4 people are just not making me try to have a bad day. But I'm not going to let you get me down. I'm going to have a good day. I'm going to have a good day. So this T asterisk goes from 0 at the surface to 1 far away, just like U asterisk did. We'll use those later. All right, now what was really important when we talked about the velocity profile was the shear stress, and especially at the surface. Well, we have an overall energy equation, Q double prime equal to H Ts minus T infinity. Have you seen that before? Where did that come from? Somebody's law of cooling. It really is, up to this point, H was just given. Now we can work towards getting H from first principles. All right, So now, right at this point, right very, very close to the surface, right in here, tell me a little bit about the fluid flow. The fluid flow is nil, nothing. It's stationary. It was no slip. All right, how does the heat get transferred in the fluid layer adjacent to the surface? Only conduction. And so we can write down how Q double prime, remember we're trying to start talking about the heat flux, Q double prime, going out into the fluid. But to get out into the fluid, it first has to be conduction only before it can be swept away by the moving fluid. So Q double prime is equal to minus K, derivative of temperature with respect to Y at Y equal to 0. Where did that equation come from? Fourier's law. Now, somebody says, you know what, to evaluate, I need this thermal conductivity. Well, is that plate made of copper, stainless steel, iron? You know, what is the thermal conductivity of the plate? Or is it the thermal conductivity of the fluid adjacent to the plate that's critical, needs to be used in the equation, Fourier's law? And that's why they put a little F subscript on the K. It's the first time you see an F subscript on the K, and you're saying, why is there an F subscript on the K? I've never seen that before. Because it stands for the, why do you think? Because a lot of students will think, I need to use the solid material thermal conductivity. No, this is in that layer of fluid adjacent to it. Well, you can use both of these, and what you get is you get H is equal to minus K of the fluid, the rate of change of temperature with respect to distance at the surface, divided by Ts minus T infinity. This doesn't look all that appealing, but we're going to use this type of equation again and again. And basically it says, that's how I can get H. That's how I can get H. I just got to get the gradient of the temperature. Analytically or through numerically, you can maybe do that. In special cases, it'll be like the slope there. It's how does T change as I move away from that plate in the fluid. It's dt dy. Well, let's say we play with this T asterisk for a minute. I left out that minus sign. So T is equal to T asterisk times T infinity minus Ts plus Ts. Did I do that okay? Did I do that okay? Okay. Do this. Can I take the partial of T with respect to Y? Okay, if I do it to the right-hand side, what do I get? That T infinity minus Ts times the partial of T asterisk with respect to Y? What happened to the derivative of the Ts? Well, Ts is a constant. T infinity is a constant. So does this math look good? So we can substitute in there, and what we find is you'll get rid of that negative sign, and you'll have the rate of change of T asterisk with respect to Y. That's what H is. Somebody else says, you know what, I want to introduce Y asterisk. That's going to be like Y divided by something. Pick a length scale. I know that this length scale was the length of our plate, L. Let's use it. So if I put an L here and I divide this Y by L, can you see that I'm okay on the math? I put L over L there. So this becomes Kf, rate of change of temperature asterisk with respect to Y asterisk, and then I have an L right there. It's getting abstract. I know it's getting challenging. But at this point, I can summarize. I can write this equation as HL divided by Kf equal to the rate of change of T asterisk with respect to Y asterisk at the surface, at the Y asterisk equal to 0, or at S. This is why maybe you didn't like fluids as much as you should have, because they introduced things like Reynolds number, friction coefficient, those dimensionless parameters. Guess what HL over Kf is? Dimensional or dimensionless? dimensionless, and they give it a name. They think, oh, there was Professor Nusselt did a lot of work in this. He actually put it in one of his earlier papers. We'll credit him. We'll call it the Nusselt number, and that's exactly what they did. So this is the Nusselt number. What is it? H, some length scale divided by K. What happened to the K on the fluid? Well, it's kind of like you took the training wheels off of your bike, right? Big day when you took the training wheels off, you could ride solo. So you just know, oh, this is the K of the fluid. All right. It's proportional to or equal to the dimensionless temperature gradient at the surface. Well, there you go. There's a lot. Here, use theta. The book uses theta, sometimes T asterisk. You can combine these two fluxes, get an equation for H. You then combine it, get the Nusselt numbers, the derivative of the dimensionless temperature with respect to Y asterisk at the surface. Thinking back to fluids, you had a big discussion between a local value and an average value. So if I go back to this knife edge plate, and X starts right there. If I wanted to plot tau S, the shear stress at the surface of the plate, as a function of X, what does that look like? Is it flat? Does it go down? Does it go up? What does it do as a function of X? No clicker on this one, we're running out of time. Volunteer first row. Does it do A, B, or C? Which one is correct profile? Volunteer first row. Okay. No volunteer first row. Third row. B, huh? C. Yes. Right? The shear stress would be very high near the leading edge and then fall off. Why don't they? Well, a lot of times they just go like this because it's kind of infinity, goes off to infinity at that point. There's a little discontinuity, whatever. Don't worry about the point. Well, what you're often interested in the average. So they'll talk about tau S at a location X. Then they'll talk about tau S maybe at a location X average from 0 up to that location X. Or they'll talk about tau S L average between 0 and L. Do you remember things like this? And then all you have to do is take that tau S, divide by 1/2 rho U infinity squared. Somebody correctly identified that grouping of terms as being called the velocity pressure or dynamic pressure. Absolutely. Now, is this dynamic pressure, velocity pressure changing as I move down the plate? Is 1/2 rho U infinity squared changing? Or is that numerator, denominator constant? It's constant. Well, but this is C sub F, isn't it? Well, I just made it dimensionless. It has the same profile as tau. And so you have the same thing. You can talk about, oh, the local C sub F at a location X, the average C sub F going from 0 up to X, or the average C sub F going from 0 to L. The local and average values are important. Well, guess what we're going to do too? You can talk about H of X. Somebody could put H bar X. Somebody could put H bar L. Actually, there's one other I missed out. I could put HL. What is that? That's the local value of the convection coefficient at the trailing edge. This is the local value of the convection coefficient anywhere. This is the average from 0 to X. This is the average from 0 to L. So we have this challenging, I know. We talk about local sometimes, and then we talk about the average coefficients, both for fluids as well as heat transfer. Guess what you can do now? You could talk about the Nusselt number at the trailing edge, the local Nusselt number somewhere in between. You could talk about the average Nusselt number from 0 to X, and not to be left out, the average Nusselt number 0 to L. It's like so many options that you can get confused, but it's hopefully the subscripts keep it straight. Here's some of them. There's our convection coefficient, local at x, local at L, average 0 to x, average 0 to L, wall shear stress, friction coefficient. Laminar and turbulent. There was a transition as you flow down that plate. If the plate's long enough, something will happen. It'll have laminar and turbulent. And they said there was one dimensionless parameter. If you told me the magnitude of, I could tell you, I could predict whether it's going to be laminar or turbulent. If the number was low, I think it's going to be laminar. If the number was high, that dimensionless ratio was high, it'd be turbulent. What was that dimensionless parameter used in fluid mechanics to distinguish? The Reynolds number. And so it was, for a flat plate, rho u infinity x divided by mu. So we put a subscript x on this Reynolds number to emphasize that's our length scale. So as we come in to the flat plate, we're measuring x. And so the further we go down, the higher the Reynolds number is. It's a function of the distance from the leading edge. All right, the magic number, the RE critical for flow over a flat plate. Somebody in the fourth row, 1, 2, 3, 4, fourth row. This is what I did before clickers. I'd call people out with my long bony finger. All right, somebody in the fourth row. You, yeah. Give me the answer now. Yeah. Oh, you're looking down at your paper, so I won't call on you, huh? Okay. I'll walk back there and grab you. 500,000, exactly. You were saved by somebody further back, one of your friends. 500,000. There's only 2 critical Reynolds numbers you need to remember in your undergraduate education. 2,300 or 2,000 if you want to round off for flow in a pipe. Remember that. And 500,000 for flow over a flat plate. That's it. So if somebody says, oh, even all the way to the trailing edge, at the trailing edge it was only 300,000 for the Reynolds number at the trailing edge. It's going to be laminar the whole way. Somebody says, no, right in the middle of the plate, it hit 500,000 and then continued to go up because X, Reynolds number has X in the definition. It starts at 0 and goes up. Well, then it's going to be laminar in the first half and turbulent in the second half, right? So you'll have a growth of that velocity boundary layer. And then what will happen to the rate of growth? Will it continue the same trajectory for the velocity boundary layer in the turbulent region? Or will it pick up the rate of growth? Or will it diminish the rate of growth? Will it look more like this or like this? Oh man, I swear I'm going to stop doing these clicker questions. All right, let's take a look. It goes as A. You're absolutely right for some percent of you. And why do the people think about C? What are they thinking about? They're thinking about the laminar sublayer. But they're not thinking about the total boundary layer. The total boundary layer grows, but the laminar sublayer actually diminishes. What's happening in this turbulent region, it's ripping in and peeling away that laminar part of the layer over the plate. That's going to be better for promoting heat transfer. You're going to rip and gouge into it and tear it away. So you'll able actually from fluid mechanics go back and recall plotting C sub F. C sub F or tau, one of them, it goes down. We talked about that. But what does it do after you hit this transition to turbulence? Does it kind of pick up and go like that? That's answer A. I've got to stop these questions. Answer B, just kind of keep on the same trajectory. Or answer C, it really just taper off. Answer C. What is this? The friction coefficient. What's happening to the friction coefficient? We stop and we grade it. And it's A. It basically is A. And you can find this classic plot. Just go back and look in your fluid book. Why is it doing that? Well, because the velocity profile, if I plot it right in here, it has like this, and then it's flat, And so I'm interested in the slope right in there. But here, I know I have turbulence, and so I plot it like this. And in here, yeah, it's still U infinity, and there's some diminishing, but not a lot of diminishing until you hit the laminar sublayer, and then it's actually quite steep right in there. So it promotes additional drag on that plate. Likewise, if you plot the nusselt number, you'll find that it diminishes in the laminar, and then it kicks up when you get into turbulent, and then finally it slows down there. Okay, so that's the way that that trend goes. For most of this chapter now, we're just going to continue to focus on laminar. When you get to turbulent, you basically rely more on empirical correlations, experimental measurements. Somebody correlated it based on a lot of measurements. So we have to come up with our boundary layer equations. These are going to be our PDEs, our partial differential equations. They're going to be conservation of mass, and then basically momentum balance, or just call it momentum. Don't call it conservation of momentum. Some people do, but it's not conservation of momentum. It's a momentum balance equation. And the last one is conservation of energy. Now, we're going to consider only laminar. We're only going to do the 2D. We're only going to do rho is equal to a constant incompressible substance, constant density. We're going to, let me think, what other assumption is there? Steady state, not transient. And the conservation of mass boils down to the partial of u with respect to x plus the partial of v with respect to y is equal to 0. There's a lot of steps to get there, but we had a fluid mechanics class, and that was one of the main themes too. You have to come up with this continuity equation. What's the other one? You have something like u partial of u with respect to x plus v partial of u with respect to y. That's my advection of linear momentum. Then over here, you're going to have some like 1 over rho with the negative partial of p infinity with respect to x. What I'm going to have is a flat plate, and there's no pressure gradient accelerating or decelerating the flow over the flat plate. In our textbook, they have this term. I'm just going to say for our analysis, that acceleration due to pressure variation, the P infinity is just constant. That's the traditional laminar boundary layer problem. And then we're going to have a nu. What's nu? What is that parameter nu called? Kinematic viscosity. Then the second derivative of u with respect to y squared. So this is our advection of linear momentum. What does this term represent? Our viscous effects. Our diffusion of momentum due to viscosity. All right. And then our conservation of energy. You're going to have u partial of t with respect to x plus v partial of t with respect to y equal to, you can have a viscous dissipation term. The textbook has it. It's rare that it's almost always negligible. It's rare that we would track it, but it's this term. Take your two hands, rub them together. Do you think the temperature of the skin of your hands changed as you progressively rubbed them together? It did. It does. And so you can have fluid churning, like beating together with the egg beater, and it will heat up. And so in some cases, it's very important. But for the introductory case, flow over a flat plate, we neglect that kinetic and mechanical energy turning into thermal energy and energy balance. And over here, we're going to have alpha, the second derivative of temperature with respect to y squared. What do you think this term represents in the energy balance? Diffusion through conduction of heat diffusion. How about this one? Heat advection due to being swept along. These equations, once this term is dropped, look very, very similar, do they not? And then we go back and we look at our governing boundary conditions, especially if we make this, we transfer this u, use u star as u over u infinity, and then we already did t asterisk or t star, t minus ts over t infinity minus ts. We turn them into dimensionless form. They become very, very similar. And out pop are dimensionless parameters. I was going to spend time doing that, but I don't think I have time. So here's our general equation. First one is conservation of mass. Second one, you just say Navier, well, both of these are the Navier-Stokes. But this one is our momentum equation. Only their x momentum equation. X momentum. Did we write the y momentum? No. And then this is our energy equation. We neglect this viscous dissipation, neglect external pressure gradient pushing or accelerating or decelerating the flow. We get these dimensionless parameters. The Reynolds number, you know by memory. Rho, U infinity, put an x there, x divided by mu. Coefficient of friction, I've written it a couple times. The nusselt number was nu. We've written it, it's h. Some length scale, x, divided by k. So we expand our list of nusselt number. Notice the Reynolds number is dimensionless, but there is no average Reynolds number. There's only your local Reynolds number at a location or at the trailing edge, but nothing, there's no average Reynolds number. All right, I was going to spend more time on this, drawing out that similarity. But let me just say that you can transform your governing velocity or momentum equation and your thermal or energy equation and get rid of this term. They already got rid of the viscous dissipation. You look at the boundary conditions. This is no slip at the wall. This is our T asterisk. It's 0. It goes 0 to 1. 0 to 1 for U asterisk. And we have the U infinity or U asterisk is 1 at free stream, likewise T asterisk. So the boundary conditions are the same, and we have these similarity variables, Reynolds, and then down here we have Reynolds times a Prandtl number. Well, what was our property of interest, nusselt, which was our dimensionless temperature gradient at the surface, or at y star equal to 0. We just did that, true? All right. What is our property of interest up here? C sub f. Okay. What is C sub f defined as? It's the tau sub s divided by 1/2 rho U infinity squared. Okay. Let me work on this for a second. Put the C sub f over 2, takes care of the half. What is tau sub s? Mu partial of u with respect to y at y equal to 0. Then we divide by rho, and we divide by u infinity times u infinity squared, true? If I put this u infinity in this equation, that becomes u star, does it not? So this is going to be derivative of u asterisk or u star. If I divide this u by L, our length scale, but then I have to multiply by L, put 1 over L right there, then it'll become the derivative of y star, and y star at the surface is 0. We have mu, we have rho, we have u infinity L. You look at this group of terms for a while, and maybe you turn your head upside down to see it. This is 1 over the Reynolds number L times the derivative of u asterisk with respect to y asterisk at y asterisk equal to 0. So you look, this is the key to the whole chapter. You look and you say, if I'm really interested in C sub f over 2, then it's 1 over Reynolds number times this dimensionless gradient of the dimensionless velocity profile at the surface. Because the equations are similar, that's equal to that one. These are the same. So if that one's, so what you have is you have C sub f divided by 2 is equal to 1 over the Reynolds number times this dimensionless grouping right here. Substitute for this temperature profile, it's the Reynolds times the Prandtl. I don't think I'm doing a great job of explaining. Instead of just the Reynolds number only, then times that nusselt number. And this is by itself is the Reynolds analogy, but then they modified it because, well, let me go to the next page. So what we had was C sub F over 2 is equal to the nusselt divided by the Reynolds prandtl. And so if I wanted to, I could say the nusselt is equal to C sub F over 2 times Reynolds times prandtl number. That's the original Reynolds analogy result, but they modify it by multiplying by or dividing by the prandtl number to the 2/3, and this is the one that's out there and used in the literature. It's modified. How did they end up modifying? A bunch of people looked at a lot of experimental data and said it fits better to that coefficient. Empirical. That's what it is. It's empirical to modification. And over a range of prandtl numbers. So I tried to give you a sense of all of the fluid mechanics, wrapped with it the heat transfer, the new parameter, the nusselt number, and then looking at similarity variables, similarity between equations, boundary layer equations, and theoretically how to come out with this analogy. What we're going to do in the next chapter is build on that. You'll come in and say, well, C sub F is some constant Reynolds to the -1/2. Boom, you put that in and now you have a nusselt correlation. Nusselt number correlation. Well, with that, I'm going to go ahead and stop and we'll start our quiz. Thank you for your attention.